Greetings out there in YouTube land, and welcome to today's big video, which will be the part 1 video in a series in which I will scratch build the amplifier that Fender never actually built, and that is a Vibro-Champ Reverb. I intend to use the AA764 blackface schematic for the Vibro-Champ, and then I have created a schematic here for the addition of a reverb tank. I'm going to use the shorter tank, not the 14-inch one, but the 8-inch 3-spring tank. We'll go into detail on the parts later, and also how this is going to fit in to the original schematic. I also made a little tube chart for it. I used a Fender Bronco tube chart, added a 12AX7, and then put up here at the top Vibro-Champ Reverb AA764. Okay, so that's going to go into the cabinet. I have already ordered and received all sorts of brand new parts for the build, transformers, foot switch for the tremolo and reverb, and tube bases, tube shields, all sorts of potentiometers and other parts. Now, this is still not all of the parts. I'm still waiting for delivery of the speaker and all of the resistors and some more capacitors. Sadly, normally Phoenix is a 2-day delivery for me, but the post office, in its great wisdom, sent the entire shipment to Alabama. Okay, so we're going to have to wait a little while, but so what? We're not ready for them anyway. And instead of flapping my gums for 30 minutes about what's going to happen, let's just start making it happen. And the first thing we'll discuss will be the cabinet that I bought on eBay for our scratch-built chassis. I've been looking for a suitable cabinet to receive the scratch-built chassis, speaker, and reverb tank, and I was watching eBay closely, and every time I bid on one, I'd get outbid, where people would bid the empty cabinets up to higher than you could buy the amp for. But I was finally able to get a, which as you see here, really nice Vibro-Champ cabinet on eBay. Now, I had to replace the hardware here on either side, the brackets for the handle. I had to buy the straps to mount the chassis, but otherwise, pretty much everything is as it came. It's got a really nice kind of aged, perfect grill cloth, the Fender logo. Let's turn it around and take a look at the rear. And here's the rear view. You see it has the early style upper panel, which I wanted. The regular lower panel. We're going to remove these in just a few minutes and clean up the cabinet and glue in that tube chart. But just a couple words now about what I did to clean up the Tolex and make it presentable. To clean it, I use the Car Guys Super Cleaner. Spray it on, go over it with a toothbrush, then wipe it off with a clean towel. You'll be amazed at the filth that this will remove. Then after that it dried completely, I sprayed the Tolex with the Armor All Extreme Tire Shine, which has a silicone in it, and it's clear, and it goes on real shiny. You'll think, oh my God, I made a mistake. It looks kind of oily and shiny. Give it about 10 or 15 minutes though, and it soaks in and gives you a really nice glossy finish. And it's probably good for the Tolex. So that's how I got the cabinet to look like this. As I mentioned, the hardware was touched up, but otherwise I had to glue down some corners. But now let's remove the back and get started on the inside of the cabinet. And with the back doors removed, we can see that we've got a really nice solid cabinet, but pretty filthy. So let's clean the floor of this and the walls and just get it presentable to receive the new chassis when it's constructed. For the floor cleaning, I'm going to shift to simple green, which can cut grease and oil quite well and leaves a really nice smell, which is always pleasant in kind of a moldy, musty old cabinet like this. So I'm going to spray it on, scrub with a toothbrush, and then clean it off. Also, we'll have to glue down the Tolex back here that's lifting. And here we have the nice clean interior. I think this is some type of contact cement or something that was slathered on to the inner wall to hold a tube chart. I don't think that's the way Fender did it. I'm going to remove all that and install the tube chart I made a little higher and in a more normal place. For now though, let's focus on gluing down all of the loose Tolex. So now we have the interior all cleaned up and all that ugly glue off the side. And the next step is going to be to enlarge the speaker hole. This was for an 8-inch speaker, and I'm going to install a 10-inch speaker. I think honestly that 10 is about the minimum for really good tone, and there's room here to do it. So it's not going to be easy, but I'm going to press out the studs that hold the speaker, enlarge the hole, and then drill the studs in at a larger diameter to suit the 10-inch Jensen speaker. I've drawn an 8 1/4 inch circle, which will be suitable for the cone of a 10-inch speaker. The 10-inch speaker is going to reach from about here down to the bottom of the baffle, and that will allow for the chassis to slide in and out. Now I'm going to use a saber saw, one of my least favorite tools. I'm going to drill a hole on the inside of the circle and then start cutting. I can't continue down here, so I'll do the majority of it with the saber saw and the rest of it with a pneumatic saw. Okay, and keep your fingers crossed. As promised, I cut almost all the way around with the saber saw, and now I'm going to use a vertical metal cutting pneumatic saw, which I believe can finish off this final cut right here. We'll find out in just a few seconds. If you hear lots of cussing, it didn't work. The hole for the 10-inch speaker has been cut. Came out pretty good, I think close enough, and I sealed that cut edge with Titebond 2 glue and then painted everything flat black so there'll be no reflections coming through the grill cloth. I'm going to drill the mounting holes for the speaker after it arrives, if it ever does. The Jensen C10 speaker finally arrived, and as you can see, there's just barely room for it in the cabinet, but I really think that it's worth it to go with this larger speaker. Now it's time to drill the holes for those studs that will allow us to attach the speaker to the cabinet. Well, I drilled and countersunk each of the holes. They're slightly undersized so that the Phillips head screw studs can be threaded in and have resistance as they pass through the wood. The screws are all in place, and what I'm going to do is put super glue on the last ½ inch of threads before I screw them all the way in, and that way they will not tend to unscrew when the nuts are installed on the end when the speaker is being installed in the cabinet. The screws now have been super glued in place, and I've touched up with flat black paint so that there can be no reflection through the grill cloth. Now we'll flip the cabinet over and make sure the speaker fits and then we can continue with our chassis building. Well, it appears that the speaker fits up just right, so now we can proceed with our next project. To take precise measurements for the chassis, I had to put the grill cloth baffle in place because it protrudes up a little bit from the cabinet down here. So now we're going to take a measurement from here to get our overall height of the chassis. And we have to be mindful of the slight reduction in clearance due to the electromagnetic field shield that's stapled into the roof of the cabinet. So I think it's probably best, I'm going to cut a piece of wood to the exact size that I think will fit in here, and a little tiny bit smaller to allow for clearances when the chassis is installed, and then we'll see if it fits. Okay, it's kind of hard to make measurements in a three-dimensional situation like this. I've made a 1 13/16 inch block here that seems to have probably about a 1/16 of an inch clearance between the grill baffle and the top of the cabinet, with space for that shield. So I think that's probably going to be the height of the chassis. Now for the distance from rear to front, I had to put in the upper back panel because remember the chassis comes up against it or very close to it. So that will be our limiting factor at the, and it looks like to get up to a little bit short of the middle of the grill baffle and to leave a little room at the rear, we're looking at about 6 1/4 inches for the front to back maximum measurement. And it appears that the angle of the bend for the front control panel will be about 70 degrees. Since it's really tough to get an accurate measurement from the middle of the grill baffle up here to this part right here of the roof of the cabinet, I dusted off my old high school trigonometry. I probably took it in college too, but I honestly don't remember it. And we will use the relationship of the sine, which is the ratio of the side opposite over the hypotenuse, which is the sloping control panel that we're trying to get a measurement for. Okay, and when we look up the sine of 70 degrees, it tells us that the ratio between this side and this side is 0.93969. So we'll divide 1 13/16 by 0.93969 and we get 1.9288, which is a little less, a tiny bit less than 1 15/16. So this sloped control panel is about 1 15/16 inches long. For those who scrolled ahead, now is the time to start watching again. And it appears that the width of our chassis will be a little less than 15 1/4. Let's say 15 3/16. Probably a better way to determine the width of the chassis is to use that one of the back panels, and it fits in with just enough leeway. Let's see exactly how wide this panel is. It's exactly 15 1/4. So let's use that as our width for our chassis. I made a cardboard mock-up of the cross-section of the chassis with all dimensions, angles, everything identical to our measurements. And as you can see, it fits in really well. The leading edge is parallel to the cabinet edge. We're bisecting the speaker, the grill baffle. We've got a little bit of space up at the top and on the right. So I think our measurements are correct, and I think we can continue using aluminum to form our chassis. I cut out a piece of 3/32 thick aluminum which is 1/32 thinner than I normally use. It's plenty strong, and it might be a little easier to work with. And I cut out a piece that was 15 1/4 for our width, and I added up all the dimensions and came out with around 11 inches from front to back. So we'll start bending across this way. We'll bend, bend, and form our chassis. It's time to start bending the aluminum. Step one will be the little 3/8 inch flap that's on top of the rear panel of the chassis. It's once it's folded, it will go up against the roof of the cabinet. I have my sheet metal brake, in this case aluminum brake, set up with that flap adjusted, and I scored down the 3/8 inch line with the cutoff wheel to make this bend better with a smaller radius. Small bends like this of only like a fraction of an inch are extremely difficult. So hopefully that inscribed line will help the metal bend cleanly. The upper lip here is bent to 90 degrees. Now it's time to do the bottom bend for the rear of the chassis. Again, I have scribed the bend with the cutoff wheel probably a third or quarter of the way through the aluminum. I stopped here at 45 degrees so you could see how well this aluminum brake is working. If you look down, it's perfectly straight all along here, which is very important. You don't want it to be bowed. So let's finish our 90-degree bend. Checking to see if the bend really is exactly 90 degrees, and it's a wee bit short. So what I find is I have to bend past 90 and then let the metal kind of, the elasticity of it, draw it back to exactly the 90 that I want. So I'll do that now. And now we're at exactly 90 degrees. Well, we've got about half of our chassis formed. Now I'm going to have to bend this 3/8 inch lip here first, and then we'll do the 70-degree bend to bring that front panel around at an angle, as it is on just about every Fender amp. Since the front panel is inclined at 70 degrees instead of perpendicular at 90, the little flap here at the top can't be at 90 degrees. It has to be at 110 so that it is parallel to the floor of the chassis with the front panel tilted in at 70 degrees. According to my trusty protractor, this top flap here is exactly 110 degrees compared to what will become the front panel. Okay, so now I'm going to bend the front panel backwards so that the angle with the floor inside the chassis is at 70 degrees. Now we're ready for that 70-degree bend of the control panel. It's time for the acid test to see if the chassis will fit in the cabinet, and it's exactly as planned. We've got slight clearance at the top and at the bottom, and it fits in nicely, and the back panel fits in quite well with the chassis up flush against it. So I'd say that it was a major success, and now it's time to move on to... It's time to lay out the control panel. We're going to have a high and low input jack, volume, treble, bass, intensity and speed for our tremolo, and finally our reverb intensity control. Have our Carling on-off switch here and our pilot light. I first lay out the controls to where there is sort of a pleasing balanced appearance to it. Now I'm going to go back and mark on the tape. I put tape over the aluminum and mark specific distances, like this distance from the edge to the center of the input jacks will exactly match the distance between the edge and the center of the pilot light, and all of the knobs then will be equidistant and balanced between the toggle switch and the input jack. So let me do that. And where would I be without my trusty sidekick Mitzi to help me in the construction of this amplifier project? Mitzi, are you a good girl? Meanwhile, Jack is slithering around down here by my feet, trying to get me to let him go outside and play, which he never gets to do. I've marked my centers and included the dimension so that there's no mistakes made on the diameter of the hole that's drilled. And now it's time to go out in the workshop and drill the holes this size. Then we'll flip the chassis over 90 degrees and we'll start to lay out the underside. I'm out in the workshop and I have drilled 1/8 inch pilot holes at each of the intersections of the horizontal and vertical lines. And now it's time to use the properly sized bit to go in and create openings that are appropriate for each of the components. The holes are now drilled in the control panel. I tried fitting each of the components into their respective hole. These two had some interference, so I used a file to kind of clean up the inner perimeter to allow the components to fit through freely. In case you're wondering why I bent the chassis first and then did the machining, there's a couple reasons. Number one, what a shame it would have been to go through all the trouble to do all the machining on the aluminum and then have the bending not come out exactly right and then have to repeat everything. As it stood, I would have to repeat the bending if it didn't fit, but I would not have to repeat the machining. Second, what may appear to be a center line when the panel is flat, once it's bent, it could be a little bit above or below center line, so I preferred to do my layout on the final panels themselves rather than on the flat piece of aluminum that was unbent. Now it's time to flip the chassis over and we'll start doing the machining here for the tube sockets, transformers, and all the other components. We have to be concerned when we're doing this that there's clearance for the speaker. So what I'll do is mount the chassis in the cabinet with the speaker and then show the depths that are permissible here on the chassis floor down to the speaker so that I won't exceed that distance and have the chassis actually come in and bump, or pieces attached to it bump into the speaker itself. I learned all these little secrets the hard way, okay, over the years through bitter experience, and I'm sharing them with you now to try to help you avoid having to experience them yourselves. I think it's time to take a break from wrestling our aluminum chassis to having a schematic review of the AA764 Vibro-Champ, and then to explain how I intend to insert a reverb circuit into it. Our circuit begins here with the routine Fender high and low gain inputs into the grid of the triode of V1A, which is a 12AX7. It's cathode biased. The plate then feeds the tone stack, which consists of a bass and treble control. The signal exits from the treble control through the wiper, and as we will see, that is where I'm going to take the dry signal from this circuit and send it to my reverb, and I will return it after the volume control into the grid of the second triode of V1, which would be V1B. From there, the signal is going to travel through the coupling cap over here to the grid of the 6v6 output tube, and then output the signal to our now 10-inch speaker. Originally it was 8-inch and 8 ohms. Ours will be 10-inch and 10 ohms. We see that the filtration here is with 20, 20, and 20 microfarad filter caps. Rectification is by a 5Y3 GT, and our tremolo circuit is fairly standard. We have the fairly standard tremolo circuit down here, which uses the first triode of V2 as the oscillator loop. It's the typical type of oscillator circuit where the signal will come out of the plate, go through a 0.02 microfarad cap, a generally 1 meg resistor, 0.01 microfarad cap, another 1 meg resistor, and down here through a 0.01 microfarad cap, 1 meg resistor, and then back to the grid. And the input here will send another signal through here. And the speed of oscillation is controlled by the values of the 3 capacitors and also the values of the resistors that are positioned in between each of those capacitors. Our tremolo speed control is right here, and the way it works is one of those fixed 1 meg resistors has been replaced with a 3 meg reverse audio potentiometer, and that allows us to vary the resistance between these two capacitors. Also, to keep us from being able to crank this down to 0 resistance, there is a 100K resistor in series. Okay, this then will protect us from going too low on our speed control and actually stopping the oscillation. Why does a variable resistor work here to alter the speed of the tremolo? Let's take a few seconds out here for a new feature in our video and see if we can't explain it. Which brings us to a special feature in today's video called Jack's Geek Fest, which will enable viewers who would like to go into a little further detail on a complex subject to do so. So let's get started. Here is a diagram of the oscillation loop that's found in almost all Fender and most other brands of amplifier. 3 capacitors in a loop with resistors in between each. The frequency of oscillation can be easily determined by this equation, in which it is equal to 1 divided by 2 pi times the square root of 6 times the resistance times the capacitance. All that sounds real scary, but 2 pi times the square root of 6 is a constant. It's 15.4. So instead of putting all this, let's just write 15.4. Okay, a line, and it will be divided into 1. Now, how do we get this value? Well, if your resistance is 1,000,000 ohms, and it almost always is, and your capacitance is like 1,000,000th of a farad, in other words, microfarads, then the millions cancel out, and all you have to do is enter the capacitance in your loop as microfarads. So in our loop we saw we had 2.01 microfarad caps and a 0.02. Let's just, for simplicity's sake, just say 0.01 down here. So 15.4 times 0.01, when we multiply those together and then divide it into 1, gives us 6.5 cycles per second, so that for every second that passes, our tremolo will oscillate 6.5 times. Now, what if we replaced all of the 0.01 microfarad caps in our loop with 0.02s. Well, you can see that that will double the denominator, which means that we would end up with about 3.25 cycles per second. So one observation that's important here is the way to slow down the loop is to either increase the resistance or increase the capacitance. One of the rules in math is as the denominator of a fraction increases, the overall value decreases. So we can say then that the frequency of our tremolo is indirectly related to 1 over the resistance and the capacitance. As these values go up, the frequency goes down. As these values go down, the frequency will go up. So if we wanted to speed up our oscillation loop, which we really won't when we're dealing with tremolo, but if we did, we could go to 0.005 microfarad caps and end up with a 13 hertz tremolo rate. Okay, normally we slow it down, and this is why by increasing one of the 0.01s to 0.02, you increase this number, we slow down the tremolo. In our case, we're going to put a variable resistor that can go from 1 million ohms to 3 million ohms, and by increasing it up to 3 million ohms, we will slow down the frequency of our tremolo. So I hope this makes it clear, and if you ever have trouble remembering how do I slow down my tremolo, just remember that the frequency is indirectly related. It goes in the opposite direction of the change in either the resistance values or the capacitor values. And that's it for today's chapter of Jack's Geek Fest. I hope that some, if not all of you, have gained increased understanding of a rather complex topic. We feed the signal out here to the second triode of V2, which will amplify the oscillation signal, which is going to be from about, 2 or 3 cycles per second down to maybe a half cycle per second. It's sub-audible, and that's why we can feed it into our amplifier circuit and not hear it. I get asked that all the time. How come we can't hear the tremolo oscillator? Well, it's down at like 3 or 4 cycles per second. Okay, so we will come through our tremolo intensity control here, which is sort of like a volume control. We'll send more or less of our oscillator signal up here to the cathode of the second triode of the 12AX7, another preamp tube, and we'll modify the bias of that second triode and therefore give us the volume oscillation that we associate or call the tremolo effect. Okay, now that's the way the Vibro-Champ works. Now let's discuss how the reverb effect is going to be inserted into this signal. And as we've already discussed very briefly here, I'm going to take the signal output from the treble control. Now that's the entire signal is passing through this wiper. We're going to take that entire dry signal and send it to our reverb circuit, and then we're going to return the wet signal from the reverb circuit up here to the grid of the second preamp triode. You see where the two insertion points are. Now let's look at the schematic for the reverb itself. Now this is my hand-drawn schematic of the circuit I propose to add to the Vibro-Champ to give us a reverb effect. Now I will make a photo of this and put a link in the video description that will lead you to a place where you can download this schematic if you decide that you'd like to make your own Vibro-Champ Reverb circuit. And we see here that where the A was marked on the Fender schematic, we're bringing our dry signal in here that's coming from the wiper of the treble control down here to a 2 megohm potentiometer. And this will serve as a volume control, or what we'll call an intensity control, for our reverb signal. And we bring it down here to the grid of another, this would be V3A, the first triode of the third 12AX7. And we'll take the plate signal and run it through a reverb driving transformer. One end is connected to the plate, the other is connected to the B+, and I'll find a place in the Fender circuit where I can get like 225 to 250 volts of B+. Go through our reverb driver transformer, and then we'll go through our shielded cable, which will go to our 8-inch 3-spring tank, which I've identified right here. And the signal will go through and gain that reverb effect, and then come out through another shielded cable into the triode of V3B, the second triode of the third 12AX7. Now, something very important here that people don't pay attention to is that one of the jacks into the reverb tank has to be insulated from the tank. The other one, the shield, is going to be grounded to the tank. So I'm going to use on my input shielded cable is going to come in here, and that will be insulated from the tank. The signal is shielded and it's grounded up here at the transformer end, so I get no noise. And then I'm going to use the shield of the output from the tank to actually ground the tank itself to silence it. And you see here where the shield itself is grounded and the shield is connected to the tank. Now, why, you ask, do you not want your shielded cable to be grounded at this end and at this end? And that will create something you've heard of called a ground loop. And that is that you do not want two parallel wires, in this case the shield and the wire within, running parallel for any great distance through your circuit, for fear that a 60 cycle hum signal may set up in the shield and through capacitance feed that 60 cycle hum into the signal in the wire. So we do not want a direct connection from here to here, and we break it up by having the shield not be connected to the tank. We pick up the tank over here on this shielded cable, take it directly to ground, and the signal within goes over here to this triode. I've had viewers ask me, why does my reverb hum so loud? And I ask them if the shielding for the input cable is grounded to the tank as well as the shielding for the output cable. And if it is, that's probably the cause of the hum. Okay, so just a little diagnostic information there. Now let's move on. The signal will be, this will be our wet signal from our reverb tank, comes out here through our coupling capacitor. And we have our foot switch over here where if I step on it, it will ground the signal and will silence the reverb. And the signal then, with as long as that switch is open, will come up here through a 1 megohm resistor and be fed into the grid of our second preamp triode. Right. Now, the one thing I failed to mention when I was discussing the Vibro-Champ schematic was how the foot switch operates to turn on and off the tremolo effect. And there's a lot of confusion, I think, in made primarily by the fact that there's two completely different types of tremolo found in Fender amps. The one type of tremolo that uses an opto-isolator, that little flashing neon light with a photoresistor, you will find in higher wattage amps like the Deluxe Reverb, and the larger circuits will use that, and it varies the volume of the signal being sent to the output tubes. This type of tremolo is quite different. This is not a volume modulating tremolo. This is a bias modulating tremolo, and it will alter the bias by feeding voltage on and off here to the cathode of V1B, the second triode of the 12AX7 preamp tube. So as we vary the bias of this tube, the volume of the signal as a result will be altered and will give us our tremolo modulation. Okay, so where the confusion comes in too is that the opto-isolator type of tremolo requires a foot switch to work, and the foot switch has to be in the grounded position for the opto-isolator tremolo to function. Conversely, the bias modulating tremolo, like we find here in the Vibro-Champ, doesn't really need a foot switch. It's optional. But if you have a foot switch, it cannot be in the closed or grounded position. It has to be open. If you close the switch and your foot switch, you will mute the oscillator output and stop the tremolo effect. So it operates in the circuit that we're describing here sort of like the reverb foot switch does. Giving ground will mute the signal. If this were a Deluxe Reverb, however, with the opto-isolator type of tremolo, giving ground would make that tremolo work. Okay, so you see where the confusion might be. A bunch of people who try to work on Deluxe Reverbs and opto-isolator tremolos that don't have a foot switch, they can't figure out why that darn tremolo doesn't work. Okay, I hate to admit it, but I've fallen for that a few times myself. So, in this particular case, we don't really have to have a foot switch to control our tremolo, but it's a very convenient thing to have, and I did order one so that we will have one to remotely control both our tremolo and our reverb effects. One more detail is I'm going to use an output transformer that has both 4 ohm and 8 ohm output impedance. So you can use the 8 ohm cabinet speaker, or if you have two 12-inch speakers in parallel with a net 4 ohms of impedance, you can then plug into the jack that I will connect to the 4 ohm output and have matched impedance. So you can use either a remote speaker cabinet or the cabinet speaker. Another point to consider is the negative feedback loop that runs through a 2700 ohm resistor and in here to the cathode of V1B. I will make that switchable. So we will have a negative feedback loop that can be switched on and off. I find that to be a very useful modification in almost every Fender circuit. Third point is whenever you're using an existing schematic, especially a Fender schematic, because it's real easy to tell. Up here it says AA764. Well, when they modified or theoretically improved this circuit, they would call it the AB764. And therefore, there might be some valuable alterations that you could find in the AB circuit that you might want to apply to the circuit that you're building. Now, the AB only has just a couple very small alterations. One is that they found that the 470 ohm cathode bias resistor had to be increased from 1 watt to 2 watt. Apparently heat was getting to it, so they doubled the wattage so that that resistor would last longer. I'm going to do that. I might even go to 3 watts. Who knows? What the heck? And the other thing that they did is they put a 40 microfarad filter cap here in the first position. I'm not exactly sure about that. I've had really good luck with 320s. I'm going to think about that. I'll either go with 320s or maybe a 30 there. But I'm probably not going to heed that AB modification in that position. So now that we've had a thorough review of both schematics, I think it will be clearer as I start machining the chassis to accept parts like the V1, V2, and V3 12AX7s, that reverb driver transformer, output jacks for the foot switch, for the tremolo and for the reverb, power transformer, things of that sort. We've seen now how they look in a schematic, output transformer, and pretty soon as I start wiring, you're going to see how all of this symbolic gibberish here looks in three-dimensional actual parts being assembled in a very specific way in the chassis, hopefully to provide us with really good tone and great tremolo and reverb effect. This is probably a good place to bring an end to our part 1 video in the series, and in part 2 we will pick up with the final machining of the chassis and begin wiring and attaching all our different components, and that should be ready probably in another, say, 2 or 3 weeks. And I'd like to offer our sincere thanks to all our Patreon patrons and PayPal contributors. Without their generous support, there would be no channel and no videos. If you would like to join them in supporting our channel, I will put links in the video description which will enable you to do so. And so here at the end of our part 1 video and looking forward to part 2, I wanted to wish you all a fond farewell for now. We'll see you again in the near future, and until then, stay happy, stay healthy, and stay tuned. Bye for now.